Should I stop? Should I stop this one? Okay. Thank you.
So our second presentation will be my fellow colleague, Péter Füri. He will talk about lung diseases, the effect on the airway deposition, distribution of the radon progeny. And we start soon already.
Thank you very much for the kind introduction. And I'm Péter Füri from the Center for Energy Research, Budapest, Hungary. And I will speak about how lung diseases, asthma and COPD, affect the airway deposition distribution of the radon progeny. It's quite a complex task. I was investigating it and just wondering that how complex an airway disease is. And so first, I would like to teach a bit pulmonology because it's important to know how our lung and our respiratory tract looks like. It was also mentioned in the first presentation that there are upper airways, there are bronchial airways, and there are acial airways. But our model has much better resolution than the HRTM. We have airway generation resolution, so we can the levels of the bifurcations. We can simulate the levels of the bifurcations and calculate the deposition distribution at every level of the bifurcation. And it's important that exothoracic airways have the main function to filter out the biggest and the smallest particles to protect the lung. Bronchial airways are the conductive part, and the acial airways are the part where the gas exchange happens. And the bronchial airways are the most important in the case of dosimetry because the highest doses are there. So I'm only calculating doses for the bronchial airways. And now I would like to highlight how lung diseases influence our lung. So unfortunately, asthma is quite common. Many children have asthma, and its effects are inflammation of the airways, narrowing of the small airways, and contracted bronchial airways, and the mucous layer is much thicker and much slower. So the people start to cough, wheeze, shortness of breath, and feel chest tightness. But fortunately, asthma is now good curable with inhalators. In contrast with that, COPD is much worse. So for COPD, in addition to this, so the bronchial contractions, the acial airways are also contracted and the wall of the alveoli is destroyed. So if you get COPD, it can only get worse. At the end of it, if you are not cured, you will die. And the main causes of COPD are air pollution and smoking. Mostly smoking, but many people get COPD in developing countries because they use coal and they burn everything. So air pollution is quite a big issue in the developing world. So it's how it affects the breathing pattern. This is one of the most important difference between a healthy subject and the people with COPD, that as you see, for healthy people, the tidal volume is quite small, 500 cubic centimeters. But as the severity class goes worse, so the people get more sick, the tidal volume increases. As you see for class 1 to 2, the tidal volume is more, 625 cubic centimeters, but for class 3, it's 1,200. And the frequency is also increasing, as you see. So for a people with COPD inhales much more radon progeny than healthy people. Okay, and I will use deposition fractions, and that is the ratio of the deposition per inhaled particles. But for dosimetry, we need deposition rate, so we need the number of deposited particles for unit time. And it's important to note that deposition rate can be higher even if deposition fraction is lower. For example, for class 3, there is quite a fast breathing, so there is no time to deposit. The deposition fractions are partly smaller, but the rates are always higher for COPD because of the more inhaled air. Yes, and now I would like to highlight how particle diameter influence the deposition pattern of the particles. As you see, I made my calculation from 5 nanometers to 5 micrometers. The smallest particles So the unattached progeny deposit with very high probability in the upper airways and in the bronchial areas. Probably in the reality, no one gets into the acinar airways. They deposit with almost 100% probability in the bronchial and the acinar, in the extrathoracic airways. But the attached progeny have a few hundred nanometer diameter. They deposit with quite low probability everywhere. So they are inhaled and they are exhaled. As you see here is that middle, it's quite low deposition, and they mostly reach the deep bronchial airways. Yes, and the three main deposition mechanisms are diffusion, sedimentation, and impaction. Of course, for the smallest particles, diffusion is dominant, but then sedimentation comes also very high. And for the biggest particles, for example, for aerosol medicines, impaction is victorious. Yes, and how COPD impacts the deposition? As you see, for class 1 or 2, the difference is not so big, but a bit also higher inhaled rare volume. So the airways are also narrower and more air is inhaled, so there is less time to settle down because there is higher air velocity. But the higher air velocity results also in that way that the particles go deeper in the lung, so less is exhaled. And as you see, as a result of these two things, both the bronchial and the acinar deposition is more for COPD, also for the smaller, also for this weaker severity class, but for class 3 it's almost more. Yes. And now I would like to highlight the airway generation specific deposition of the attached and unattached progeny. This is for a healthy man, and as you see, the unattached fraction is very small. So they mainly deposit in the upper airways, so 93% in the upper airways, and which not deposit there, they deposit in the first few bronchial airways. In contrast with that, the attached progeny deposited very low progeny in the upper airways with 5.5%, and they go deep into the lung, into the in the small bronchial airways, and into the acinar airways. Yes. And how COPD affects the airway generation specific deposition. As you see, there is a low bronchial contraction that I used, 15%, but a very high acinar duct contraction. And that's why here in the bronchial respiratory, do I have it? Igen. Csücskedje vissza kéne menni. Thank you. So the bronchial contraction also has an effect, but here is the biggest contraction. So in the acinar airways, so in the bronchial respiratory, quite much progeny deposit. But for dosimetry, the bronchial deposition is important. As here you can see, the bronchial deposition is also more for the COPD. And as we go to bigger severity class, more progeny are inhaled, and also the deposition fraction is more. So much more radon progeny are deposited in the bronchial region of a subject with COPD than for healthy people. So this will have a huge effect on the bronchial deposition, and also again the bronchial respiratory for class 3 is even more significant. How many progeny deposit here? Yes. And here I would like to, for now, I only changed the breathing pattern. The contraction was the same. Here, I also changed the contraction, because if you get sicker, you get bigger contraction. And as you see, as a synergistic effect with the breathing pattern, for higher contraction, higher deposition is. So it's another factor that enhances very much the deposition for COPD. And that's why, because of the contraction, the distance is small, so sedimentation and diffusion is enhanced. Yes. And now I would like to switch to dosimetry. That the most important parameters that are influencing radiation burden are the number of alpha decays in one airway tube, the hit probability of the target cells, and the mean absorbed energy from one hit. And it's important to mention that the first part of the bronchial airways are quite small in number, because the first airway generation has one mother tube and two daughter tubes. The second has two mother tubes and four daughter tubes. But in the 21st airway generation, you have two on the 21st daughter tubes. So in the small bronchial region, there is a small number of alpha decays in one tube, but in the small bronchial region, the heat probability on the target cells and the mean absorbed energy is much bigger because the airways are smaller. So the target cells will be much more in the short distance to the alpha emitters. And the mucous airways, mucous thickness is always the mucous layer has a strong effect also on the heat probability and the average absorbed energy, because if the mucus is thicker, the distance is more, so it has some shielding effect. Yes, and here I would like to highlight those distributions. As I said, here is a very small number of airways. Here is the second airway generation number, but as we go deeper, more and more airways are there, so the number of alpha decays in one tube will be less, but the average energy and the heat probability is increasing, so that's why we have this peak here. And in addition, the attached progeny also deposits here. Yes, and comparing the dose rates for a healthy man and for a asthmatic, for a COPD patient, it's worth to notice that the dose rates are much more even for class 1 to 2. So the contraction and the more deposited progeny has a very strong effect on the dosimetry. And for COPD, the mucus is 3 times thicker, so it has some shielding effect. But because the progeny is mixed randomly in the mucus layer, it cannot compensate the contraction and the bigger inhaled progeny number. So the dose rates are much more for COPD. And comparing class 2 and 3, the difference gets even bigger. So for COPD with class 3, there are horrific big doses, so very big doses compared to a healthy man. Yes. And it's just a notification that also these calculations were the same for the same contraction, but only the breathing pattern was changed. But now I started also to change the contraction, because if you get sicker, you get bigger contraction. This upper panel is for severity class 1 or 2, and this bottom panel is. Oh, no, sorry, but both panels are for severity class 1 or 2, but this is for attached progeny and this is for unattached progeny. And as you see, the more contraction results in more dose, even for the same breathing. So the contraction is has a very high effect on the absorbed energy and also heat probability. So it's important to model the health status of the patients. Yes. And our last comparison, but my last comparison was the mucus thickness. This was for severity class 1 or 2. I modeled normal mucus and thick mucus for COPD. And as you see, as you can see, the thick mucus has some shielding effect, but it's not so strong as the dose elevating effect of the COPD. But it's also important to model the airway generation specific mucus thickness for COPD. Yes. And as a summary, I would like to say that lung diseases have a strong effect on the breathing pattern and the airway geometry too. So for COPD, you inhale more and more progeny. And the airways are also contracted. So more particles are deposited, and also the dosimetry gets worse. So also more energy will be absorbed in the radiation sensitive cells. Yes, and the mucus has some shielding effect, but it cannot compensate the dose elevating effect of the higher deposition and the contraction. Yes, and the health status of the subject is very important here on dosimetry. And it was not in my presentation title, but I would like to highlight that not only health effect, that has health status, but also age can influence very much the dose. Here I made simulations for an adult and for a child, for a 5-year-old child. And as you can see, the child has a lower tidal volume, but much higher frequency. That child is, of course, smaller, so their airways are also smaller. And for child, the mucus layer is thinner and slower, because if the airways are smaller, so it has to be slower and thinner. And as you can see, for child, less progeny are inhaled, but due to the smaller airways, the deposition fractions will be higher, and due to the contractions, the doses will be also higher. So both for the attached and unattached progeny, inhaling the same air in the children's airways will be higher doses. Yes. And it's important because the children are also more radiation sensitive. So I don't recommend to go to a radon spa for children, because they get higher doses from the same exposure. Yeah. Thank you very much for your attention.
Thank you, Peter, for this interesting presentation. So we have time for questions.
And now? Okay. Thank you for your presentation. You told us that in the mucous layer, there are decaying progeny randomly distributed. And my question is, they are uniformly distributed due to the depth of the mucous layer, or somehow specially?
Yes, they are uniformly distributed. It's a random number generator, just so.
Thank you.
Okay. Any other questions? There.
Yes, in the frame of Radon project, I investigated the effect of individual characteristics of the subject, and one of them was the health status. It's very important, very important. We are different people, and it matters much in the dosimetry. Yes.
Yeah, I noticed in your figures that often the basal cells get a much lower dose than the secretory cells.
Yes, but because they are much deeper.
Yeah, so I was wondering, how much deeper are they in your models? What distance are you using in your models for the distance between a basal cell and a secretory cell?
I use the Mercer data. So the basal cells are much deeper. They are often not reachable from the alphas. They are much deeper. Yes.
There's a question in the chat. Could you explain why the health effects for smokers are higher than for non-smokers?
Health effects for smokers, I think it's quite complicated, but they get bronchitis, so they get contracted airways and they get a bigger deposition. So it's elevating the dose too. But also the cigarette can have some other effects, so chemical effects. But I think mainly because of the altered geometry. It's caused, but. For smoking, it's quite complex task.
Thank you. It was a very interesting. But if I understood correctly, so all results are just based on a kind of the simulation, yes?
Yes.
And did you try, or did you think that to check this model by some measurement?
I was validating the deposition pattern. So the deposition was validated with measurement data, and also with the LUDEP, other deposition model. But the doses cannot be validated because it cannot be measured in every generation.
But I think that just exactly about the activity concentration of the radon progeny in some fluids from the pulmonary tract. because I know that, so I'm not the medical doctor, but I know that for some tests and evaluation of the current state, so it is the methodology, and it is there is the possibility to just to collect the different fluids from the different parts of the pulmonary tract. So, and then it is a possibility just to measure, and then we will know what is the real activity concentration, and then we can calculate the real dose, not only by the simulation.
Yes,
Maybe for the further project.
Yes, and the main problem is that the airways are so small in the deep lungs, so it just cannot be investigated by CT or also by surgically, because they are 1 millimeter or even less. So they cannot collect nothing from that. From the big bronchial airways, yes, I think it can also make it. My idea was to use the gamma radiation when the polonium decays. So it's alpha decaying, but it also has some, I think, some gamma radiation, or some decay chain parts have some alpha gamma radiation, and it could be measured. But also the resolution, resolution of the measurements are not enough to do anything with the leap. In the big bronchial airways, it's working, but in deeper, it's not working. We tried it. We do literature research, but also for deposition, there are only regional data is total and regional data, not airway generation specific data.
All right. Any more questions? Then thank you.